Hello, everyone. It's me, Mourad Sultan Ezouidi, the professor, and today we are about witness to witness breakthrough in mathematics. For centuries, mathematicians believed that finding exact solution to polynomials equations for or of degree 5 or higher was impossible. Abel's theorem told us the door was closed. But what if I told you that today we are opening that door, that we are going to construct, not approximate, the exact roots of seventh and eighth degree polynomial equation using pure algebra, symmetry, and Ezouidi theorem. This is not, in fact, theory alone. It's verifiable, it's symbolic, and it's published. Today we will see exact roots spread from radicals and roots of unity, fully satisfying an equation classical method failed to solve. Let's begin. I will give you the common to the power 7 and to the power 8, and we are going to solve this in front of you. I will share the screen with you, my kids, so that you can fully see the picture. Okay. So I already shared this with you. Okay. Yes. It comes. So this is my kids and my colleagues and my teachers. This is the polynomial to the power 8. We are going to solve this. You can see here the first coefficient of the x term raised to the power 8 is 1. And the last coefficient is 0, means this is in fact the seventh degree form of equation. But we extend it so that can be solved. Okay? So this is the point to the power. In fact, is 7. We extend it, we see the last term. Now we'll give you the method or the Zuidi theorem, and we'll apply it. Okay? So let's see. This is our
Okay, so you brought us a really
polynomial
fascinating document today. It's
to the power 8.
deep in the world of mathematics, right? Specifically looking at polynomial equations.
That's right. Think complex formulas, lots of variables, and that classic challenge finding the roots, the values that make the whole thing equal zero.
Exactly. And for this deep dive, our mission really is to kind of wade through this mathematical landscape with you, our listener.
Yeah, we want to pull out the key ideas, figure out what problems they're actually trying to solve, and look at the methods they're using. Some are quite elegant, maybe even a bit surprising.
It's about getting to the core of the math without getting bogged down in every single fraction, let's say.
Precisely.
So, what are the main mathematical objects here? What polynomials are we dealing with?
Well, the source really focuses on two main ones. First up, there's a polynomial of degree 8.
Okay, degree 8, high degree.
Yeah, and it's written out very explicitly. Lots fractional coefficients. We probably don't need to read every single one, but it starts px equals x to the 8th minus 1x to the 7th plus 18 over 8 squared x to the 6th.
Right.
And it keeps going like that, a few more terms, all set to equal 0.
Got it. So a complex equation right off the bat.
Exactly. And the document also shows the kind of general form. Using these coefficients, they call L sub RQ. So px equals x to the 8th minus L0qx 7th plus L1qx 6th, and so on.
Yeah.
Those fractions we mentioned, they're just the specific values for these L sub RQ coefficients in this particular case.
Okay, makes sense. And what's the immediate goal for this degree 8 polynomial? What are they trying to do?
The main goal is finding its roots. And the method they lay out involves figuring out a new set of values. They call them S sub RQ, or sometimes S sub RR.
Okay.
And these S values are derived somehow from those initial L coefficients.
So we've got this complicated polynomial, its coefficients, the L values, and the task is to find the roots by calculating these intermediate L's values. How do they actually do that calculation? What's the process?
This is where the sort of core tool of the document comes in. It's mentioned again and again. It's called the discriminant formula of Mourad Sultan Ezouidi Hism.
Oh, quite a name.
Yeah. Think of this formula as like a specific mathematical process or maybe a transformation that you apply to those initial L coefficients.
Transformation engine for coefficients, maybe. So what does this engine produce for the degree 8 case?
Well, the author applies this formula systematically, calculating these S sub RR values. And here's something really interesting that pops out.
It's that.
A lot of these S values turn out to be 0. Specifically, S0R, S2R, S4R, and S6R, all 0.
Oh, okay. That's usually a good sign in math, right? Things vanishing often means simplification is coming.
Exactly.
So what are the non-zero SR values that the formula gives them?
The document lists these. Orla is 1R is minus 10, S3R is 35, S5R is minus 50, and S7R is 24.
Whoa, hang on. Those are just integers, simple integers, compared to the fractions they started with.
Right. Remarkably simple integers. That's a key result of applying this formula here.
This is where it gets really interesting for me. How does writing the original polynomial using these simple A's values change things? What does it look like?
It simplifies dramatically because all those A's values corresponding to the odd powers of x is 0, S2, S4, S6 are 0.
Right.
The polynomial, when you write it using these new A's coefficients, only has even powers of x left. It becomes px equals x to the 8th plus s1 rx to the 6th plus s3 rx to the 4th plus s5 rx squared plus s7r equals 0.
Which, if we plug in those integers,
Yeah.
that's x to the 8th minus 10x to the 6th plus
Right.
35x to the 4th minus 50x squared plus 24 equals 0.
Exactly.
Wow. Okay. That is a huge transformation. It went from, what, 8 terms with messy fractions down to 5 terms with simple integers at only even powers.
That simplification is the core takeaway here. That discriminant formula, it's not just, mathematical busywork. It's a tool that revealed a hidden structure in this specific polynomial.
And that structure makes it much easier to solve, presumably.
Absolutely. And the document really runs with that.
Right. I think I see the pattern. X error, X error, X error. It looks like something you could maybe treat differently.
Precisely. The author makes a really clever substitution at this point. They say, let x squared equal x, a new variable, capital X.
Ah, okay. So you replace every x squared with x. That means x to the 4th becomes x squared, x to the 6th is x cubed, and x to the 8th is x to the 4th.
Exactly right. And this substitution transforms that simplified equation into something much more manageable. It becomes a polynomial in terms of capital X, x to the 4th minus 10x cubed plus 35x squared minus 50x plus 24 equals 0.
And that's just a quartic equation, degree 4. I mean, still not trivial, but way better than degree 8.
Much better. And the document provides the roots for this quartic in X.
What are they?
It says the roots are X equals 1, 2, 3, and 4.
Okay, so if x, which is just x squared, can be 1 or 2 or 3 or 4, then finding the original roots, the x values, is just taking the square root.
That's all it is. You take the square root of those x values, plus or minus, of course.
Right.
And that directly gives you the 8 roots of the original degree 8 polynomial. X equals plus or minus 1, plus or minus the square root of 2, plus or minus the square root of 3, and plus or minus 2.
There you are. Ooh. Wow, okay, that's a really clear path. From that initial complicated beast, apply the formula, reveal the simple structure, substitute, solve the quartic, take the square root, done.
It's a very neat demonstration, yeah. Shows how finding the right transformation or the right tool can just crack a problem wide open.
The document also mentions something about calculating alfact values related to these roots. Is that important?
It's sort of a further step. It shows a formula using L0Q, which was 1 in this case, and the roots we just found, the xk values. It gives some examples of the results, simple fractions like 0.25, 0.375, and also expressions with those square roots in them. It's like another layer of analysis they perform once they have the roots.
Okay, so that pretty much covers the journey for the degree 8 polynomial. But the document doesn't stop there, does it? It moves on.
It does. It pivots to a second polynomial. This one is degree 7.
Degree 7.
And again, it's written out explicitly first with its own set of fractional coefficients. And it also has a generalized form, px equals x to the 7th minus L0qx to the 6th plus L1qx to the 5th, all the way down to the constant term.
And here's something interesting I noticed you mentioned. The document points out that the initial coefficients, those L sub RQ values, they're the same values used for the degree 8 polynomial, at least up to the L6Q term.
That's a really crucial observation. That shared starting point, those common coefficients, it strongly suggests these two polynomials might be connected somehow, right? Even though their degrees are different.
Makes sense. So what's the goal for the degree 7 polynomial? Still finding roots.
Still finding roots, yes. And again, the method involves determining its set of S sub RQ values relative to those shared L sub RQ coefficients.
And let me guess. The discriminant formula of Mourad, Sultan, Ezouidi, H, and M gets used again.
You got it. It's applied systematically once more, this time for the degree 7 case, to get its specific set of S sub R values.
Okay, so does applying the formula lead to that same kind of dramatic simplification we saw before? Do a bunch of terms vanish?
Actually, no, not this time. It's different. For the degree 7 polynomial, the S sub RO values that come out of the formula are mostly non-zero.
Wow.
And they're pretty complex fractional values, too. There's even an S sub -1 R term in there.
Okay, so when the document rewrites the degree 7 polynomial using these Fourier values, you don't get that nice simple form with only even powers. You get a full equation still looking pretty complicated.
That's right. It results in an equation like x to the 7th minus 462 over 8 squared x to the 5th plus 812 over 8 cubed x to the 4th, and so on. Most of the terms are still there with these fairly involved coefficients.
Okay, this is where the documents seem to take a really surprising turn, at least to me, because right after showing this complicated degree 7 polynomial in its ES form, it says something that seems almost like a non sequitur. It just states something like, or x squared equals x equals 1 or 4 or 2 or 3, which means x equals plus or minus 1 or plus or minus 2 or plus or minus root 3 or plus or minus root 2.
Yes. And the really wild thing about that statement is that those are exactly the roots we just found for the degree 8 polynomial using that whole substitution method.
Right. It's bizarre. It's like the document says, okay, here's this complex degree 7 polynomial derived using our formula. But hey, remember those roots from the other polynomial we solved?
Mm-hmm.
It doesn't actually show how to get the degree 7 roots from this complicated degree 7 equation. It just immediately points back to the results from the degree 8 case.
It's a strong hint, isn't it? It suggests a deep connection. Like maybe the roots derived from the degree 8 case using the same initial coefficients and the same core method are somehow significant for this degree 7 case too.
Okay.
And the document reinforces this idea right away. It calculates a new set of values, calls them y sub k.
Y sub k.
And it directly links these yk values to the roots of the degree 8 polynomial we found earlier.
How does it make that link? Is there another formula?
There is. A specific one. It says yk equals open parenthesis minus L0q plus 7 times xk, close parenthesis, all divided by 8.
Okay, let me unpack that. It's using the roots of the degree 8 polynomial, the xk values, like now 1, 0, sure, etc. And that initial coefficient L0q, which we know is 1.
Right.
And it plugs them into this simple linear formula, yk equals 1 plus 7 xk 8 to calculate these new yk values.
Exactly that. For each of the 8 xk roots from the first polynomial, it calculates a corresponding yk value using this formula.
So it generates a new set of 8 values derived directly from the degree 8 roots.
Precisely. And the document lists these resulting yk values. There are fractions like 34, 138, minus 158, and also expressions involving root 2 and root 3, like minus 1 plus or minus 7 root 2, all over 8. It even explicitly points out that one value yk equals 1, which you get when xk is -1, is excluded for some reason.
Fascinating. So the overall picture seems to be use the same fundamental method, that discriminant formula, on two polynomials that are related because they share initial coefficients.
Yeah.
For the degree 8, the formula reveals a simple structure that lets you find the roots directly through substitution. For the degree 7, the formula gives different intermediate values, a more complex structure. But then instead of solving that directly, the analysis immediately loops back to the roots found for the degree 8 case and uses those roots in that specific yk formula to generate a related set of values.
It really highlights a structured approach, doesn't it? Where the discriminant formula is the central tool, but how you get to the roots or what information you extract depends on the polynomial's degree and maybe the properties revealed by applying the formula.
Yeah.
That connection it draws between the degree 8 roots and these derived Sevi values for the degree 7 case. That seems to be a key takeaway about the underlying mathematical relationships the author is exploring.
It definitely shows how applying a consistent method can lead to different kinds of outcomes, or reveal these structural links between roots, even if the path isn't identical.
Yeah.
So we started with these pretty complex polynomials. We saw the power of this specific tool, Mourad, Sultan Ezouidi's discriminant formula, to derive these intermediate coefficients.
And we saw how, in one case, those coefficients led to a dramatic simplification making root finding almost straightforward via substitution.
And for the other polynomial, same starting point, basically, same formula. It yielded a different structure, but the analysis immediately jumped to referencing the roots of the first polynomial.
And then use those roots with that specific GA formula to calculate related values, a very different path.
It really underlines how finding the right transformation, or maybe just spotting these unexpected connections, can be so crucial in math. What's the kind of big picture thought you're left with after digging into this?
For me, it's how the repeated use of one specific mathematical tool, like this discriminant formula, can do different jobs depending on the context.
Right.
Sometimes it clears a path to a direct solution through simplification.
Right.
Other times it seems to establish these surprising, very specific relationships between seemingly different sets of roots or values derived from them in related equations.
And for you, our listener, maybe think about that connection the document makes between the roots of the degree 8 polynomial x equals 1, 1, 2, etc., and those values calculated for the degree 7 polynomial using that very specific formula, yk equals 1 plus 7xk. What could that specific, almost arbitrary-looking mathematical link imply more generally about how roots of different polynomials might be interconnected, especially when they share some underlying setup or are analyzed using the same kind of machinery? It definitely leaves you wondering about a possibly deeper layer of mathematical structure there.
Thank you for listening. Here we gave you an example, 7th degree from equation, and we extend this 7th degree from equation to obtain an 8th degree from equation. We solve the 8th degree, and we go back to make the relationship between 7th degree and 8th degree using this substitution. L0 for the q plus yk divided by 7 equal L0 for the q plus xk divided by 8. So this will give you the x roots, the 7th x roots of this new 7th degree from equation. Then going to use L0 plus yk divided by 7 to obtain the 7th roots. Okay. So thank you for listening. See you inshallah next time. I will stop the recording now.